Okay, dear students, from the chapter of force vibration, today we are going to discuss the topic of force transmissibility. We will be deriving the relation for force transmission. If you remember, from the spring mass damper vibration system with a harmonic force, let this is the mass supported with the base of support through a spring of stiffness k Newton per meter and a dashpot having damping coefficient c Newton second per meter, and let mass is subjected to a harmonic force F, which is having amplitude F naught and is vibrating with the harmonic frequency sine omega t. Its frequency is omega t. Then drawing its free body diagram based on D'Alembert's principle, we have already derived the differential equation for this. The differential equation is mx double dot plus cx dot plus kx is equal to. Students, we have already discussed that in the forced vibrations due to an external excitation which is simple harmonic, let the profile of the external excitation is like this. This is F naught and it is vibrating with the frequency omega. So the time period will be 2 pi by omega like this. Then we have discussed that the equation of vibration of mass x is sum of complementary solution to and particular solution. Now this red profile of vibration shows complementary solution which is transient and is there for initial period only, and the blue profile is particular solution. This is particular solution or steady state solution, and its amplitude will be now steady at a value of a, and its frequency of vibration will be again, the time period will be same to as for the external excitation, 2 pi by omega. This is 2. So when we design the systems subjected to external excitations, we are mostly dealing with this time period, and here the solution is x is equal to xp. In the coming slides we will discuss only this solution xp, which is a amplitude having a sine and lagging behind the external excitation by a phase difference phi, and its frequency of vibration will be omega as we have discussed. Taken the particular solution xp a sine omega t minus phi. On differential, velocity xp dot becomes like this, and again differentiating, acceleration xp double dot comes like this. We substitute acceleration xp double dot here, velocity xp dot here, displacement profile x here. We solve this, we get the four forces are balanced like this: inertia force, damping force, spring force, and harmonic force. Now what we observe is the spring force has an amplitude of Ka and lags behind the external excitation by phi, and damping force has an amplitude c omega a and is ahead of spring force by an angle pi by 2, and inertia force has amplitude of m omega square a and is ahead of spring force by an angle pi, means it acts in direction opposite to the spring force. Then we derived vector diagram. What is the vector diagram? say this is the for external excitation with amplitude F naught. Then the spring force Ka lags behind F naught by phi. Damping force is C omega A. It is at 90 degree to spring force. And inertia force is m omega square A, which is in a direction opposite to the spring force. As per this equation, the four vectors we have drawn, and from this we can construct a geometry like this. From this geometry, from say triangle OAB, we can find out tan phi as AB minus OA, as well as we can find out F naught square, which is OA, F naught square, which is OA square plus AB square. We will solve this, and when F naught is OA square plus AB square, OA is spring force minus inertia force, amplitude, difference of amplitudes. AB is equal to the amplitude of the damping force. We substitute, we rearrange, A becomes like this, and when we substitute, then A becomes like this. When we substitute the value of C omega by K, and we substitute omega and C omega by K, the relation became like this. A is excess by square root term, which we have already discussed, and excess is F naught by K. So we know the differential equation mx double dot plus cx dot plus kx is F naught sine omega t. Then its solution is x, which is equal to complementary solution xc plus particular solution xp. Now we have what derived is xc. Complementary solution is when you take the right term f naught sine omega t, it is the solution for mx double dot plus cx dot plus kx is equal to 0, means damped free vibrations for an underdamped system. So xc solution is, we have derived in the third chapter, it is xc is c e raised to power minus zeta omega t sine of 1 minus zeta square and root omega t plus phi 1. Some phase difference is there. Now, particularly steady state vibrations. Complementary solution is transient vibrations. This is a steady state. These are steady vibrations, and complementary is transient vibrations. And the solution for steady state is amplitude is steady, let it is A, frequency of vibrations will be omega, let it is lagging behind by phi. Now we have already derived that A's relation is like this. A amplitude is excess static deflection to square root of 1 minus omega by omega n whole square, this whole terms square, plus 2 zeta omega by omega n, this terms square. And phi is the angle by which it will lag, so that phi is, tan phi is 2 zeta omega by omega n to 1 minus omega by omega n square. Next is, now we come to the force transmissibility, or the force transmitted to the sport. Now, mass is subjected to a force F, which is F naught sine omega t, and it vibrates like this, and that other forces, spring force, damping force, and inertia force, are shown in the vector diagram as discussed in the previous slide. Now, from the mass, due to the vibrations, spring force will be transmitted to the sport like this, as well as damper will transmit a force which is damping force. Means sport is being subjected to two forces, F spring and F damping. Now from the vector diagram we know spring force amplitude is Ka, damping force amplitude is C omega A. Both these forces are at 90 degree. So when we add these forces, the resultant force is this vector Ft, and Ft's amplitude is Ft is square root of Ka whole square, which is spring force amplitude, plus C omega A whole square. This is damping force amplitude. So it means we have derived the relation for how much force is being transmitted to the support or the base. So for certain problems, always the mass is not like this. Sometimes mass is an IC engine or a motor. Say the mass is a motor like this. It is vibrating. Then it is subjected through a spring and damper like this. And we have, so now this is the base. Now the force will be transmitted, spring force from here, say Fs, short form, damping force Fd, then the total force being submitted to the base, this is base, this is Ft. So problem can be mass can be above and support or base can be at the bottom, or support can be at the top and mass is hanging through this. Then the transmitted force is Ft. We have derived the relation. Gurdeep, is this derivation clear for force being transmitted to the support? So the next is transmissibility. It is force transmissibility. And our transmissibility ratio, it is simply force being transmitted to the base and amplitude of the force being transmitted to the base and amplitude of the external excitation. Okay, simply the ratio of the two forces is known as force transmissibility, or simply transmissibility or transmissibility ratio. Let us substitute Ft from here, and A relation we have derived is like this: F naught by K, and in the denominator we have square root of 1 minus omega by omega n whole square, this whole terms square, then C omega by K whole square. Now you substitute F naught here. Transmissibility becomes like this. From here, let us, then from here A cancels out. K, if when we take to the numerator, this term becomes C omega by K, and this K cancels out. We substitute C omega by K. The relation becomes like this, which is given as transmissibility ratio Ft to F naught. The relation is like this. This is the relation, which is in the numerator square root of 1 plus 2 zeta omega by omega n terms square, and in the denominator 1 minus omega by omega n square, then whole terms square, plus 2 zeta omega by omega n whole terms square, where omega by omega n is frequency ratio. If you remember from the topic of support motion, this is the relation for A by B. A by B is now known as motion transmissibility. But here the motion is transmitted from the base to the mass. So relation for both force and motion transmissibility are numerically same, but the problem is here in force transmissibility, mass to support force is being transmitted. But in the case of motion transmissibility, this is the base. From base, we are transmitting the motion to the mass. So both the numericals, though they may appear different, can be solved like this. Suppose transmissibility is given as 0.25. What it means is this system is having 25% transmissibility. So out of the F0 force acting on the mass, only 25% force is being passed to the foundation, to the ground, to the base, or to the support. And now let us draw the curves between transmissibility versus frequency ratio for different damping ratios, and the plot says like this is the plot for motion transmissibility and force transmissibility ratio TR, which is FT, the force transmitted to the support, to the external excitation F, or its amplitude F naught. When we observe is the transmissibility less than 1, which is the desired, is observed for a frequency ratio greater than under 2. So this is the isolation region, vibration isolation region. So we have to design our isolations in such a way that the plot is in this region. Means omega by omega n frequency ratio should be greater than under 2. Moreover, what we observe is at resonance, when omega by omega n is 1, the amplitude of vibrations will be infinity. But if we introduce a small amount of damping, say damping ratio of 0.25 is there, that we have touched the damper or dashpot, then the transmissibility reduces from infinity to 2.25. It means while designing the isolator systems, damping is very important, especially at resonance. Otherwise, transmissibility will be excessively large. So, when we design isolation system, we introduce a small amount of damping, say zeta. It may be depending on the problem, say zeta 0.25, so that if accidentally the system vibrates at resonance, then the damage to the support or base is the least. The characteristic curve of transmissibility versus frequency ratio, we observe that when omega by omega n is greater than under 2, means we are in vibration isolation region and damping is absent, zeta is 0, then transmissibility relation becomes like this: 1 upon omega by omega n square minus 1. We have changed the sign here. In place of 1 minus omega by omega n square, we have taken like this, which is required when omega by omega n is greater than 1 to keep it positive. Now, further we observe that unity transmissibility occurs at 2 points. First is when frequency ratio is 0, another is when frequency ratio is under root 2. Means these are the 2 points, this and this. When the when the system is not running, your mechanical vibration system, if you apply a force to the mass, the same force is transmitted to the support. This is the first point, but this is not the practical case. Practically, the system has to run at certain omega. So, if in the system omega by omega n is under root 2, again this will be unity. In between these two, it will be transmissibility will be higher than 1, and this region is to be strictly avoided. Next is, for the best design of the isolation system, you kindly keep your omega by omega n near to 4 or 5. How can we achieve this? The one way of achieving this is, if you can put the motor, the pump, the turbine, or whatever is your vibrating system. If it can run at high speeds, then there will be lesser forces transmitted to the base. So select the high speed equipments. If this can't be achieved and omega is fixed, another alternative is you reduce omega n. Omega n reduction means, while designing the pads or isolators, what you do, you keep spring stiffness to be low and increase the mass of the vibrating system. How can we increase the mass of the vibration system? You can put inertia block. Inertia block can be attached to the mass, and in this way one can control how much force is being transmitted to the base. We will be using the relation for transmissibility and this analysis from the characteristic curve in solving some problems in the next. Thanks, my dear students.